Okay, thanks again for the invitation. So I just want to go over this proof of the polynomial Wolf axioms again, because I went fast and I made a little mistake. So the mistake was associated to this change of variables formula. So if you know that a function is continuous and k to 1, then you know that the measure, this, you can change variables and it's the same, it's equal to this with 1 over k. Now, with, at least it has to be 1 to 1, so you know that this is always bigger. And if you know that it's less than or equal to k to 1, then you can have the other inequality. And with the k, right? And so polynomials, and so polynomials of degree d map at most d to the power n points to the same place, as long as this is non-zero, so that we're mapping isolated points to isolated points. By Sard's theorem, you can throw away the points where the points where this is zero map to a zero measure set. But when you're looking at just like if the derivative is zero, then you know that the function at those points where the derivative is zero is all going to the same place. So, which has zero measure, same point. And so, but when you're looking for just this inequality, this is bounded by the set where this is non-zero, the same integral, but removing some points, because when this is zero, it's not adding to the integral. And then you have this k to 1 property, or this dn to 1 property, so you can have this inequality, and then you can put the points back if you wish. So anyway, we have these inequalities, which we will use. And so this, I recall, is what we were trying to prove, that these are tubes, delta tubes, which all live inside the set E. And we want to prove this when E is semi-algebraic. And we have a bound on the complexity, and this constant can depend on the complexity. Now, first of all, we did a reduction using this Tarski-Seidenberg theorem. We proved, first of all, that all the lines inside E, the set of all the lines inside E, is also semi-algebraic. And so this is the position of the lines, and this is the direction of the lines. And so especially this theorem tells us that we can project down, orthogonally project onto the directions, and that is still semi-algebraic. And then also we note that we don't want to think about tubes anymore, we want to think about lines. So we think of all the lines inside these tubes, line segments of length 1 inside these tubes of width delta. There's a delta ball of different directions inside each single tube, and each tube is direction separated. So you're not getting the same directions with different tubes. So you have this inequality that you get at least as many, the measure of this, which is a delta ball, which has this measure for each direction. So you get a delta ball here for each one of these. And so this is bigger than this. This is at least as big as this. So we reduce this problem of, if we want this inequality, we just need to bound the measure of the directions of the lines by E. And so to do that, we parametrized. So a semi-algebraic set can be parametrized. So bear in mind these directions are, so this T is the height. The tubes are going up like this in this picture. So you have some D, and then and as T increases, you go up, and then you have some initial position A. So these directions, because it's a semi-algebraic set, which is defined using polynomials, it maybe isn't so surprising that you can parameterize it with other polynomials. However, it's not an easy thing to prove. And you have some kind of bound on the degrees of the polynomials and the number of pieces you need according to how complex the semi-algebraic set, this semi-algebraic set is. So because we have these nice bounds, our constants are allowed to depend on this. So when we just add up n different pieces, we just get this in the constant, which is fine for us. So now we just need to prove instead of proving that this is bounded by the measure of E, we just need to prove that one of these pieces is bounded by the measure of E. And moreover, in order to complete the proof, even though we just need to bound the measure of this, which is parameterized like this, we also need to parameterize the positions. So remember, this is the orthogonal projection of the lines onto the directions, and this is positions and directions. So now it's a vector positions and directions. And we can also parameterize that because it's still semi-algebraic. So I'm telling some lies here. I'm going to tell lots of lies today. The Gromov's algebraic lemma only lets you do this with smooth functions with bounds on the derivatives, but then you can do some Taylor approximation. You can break things up into many balls. So we lose this in the constant, this which you might not need to, but in the original Kakeya conjecture, you need to because of Kakeya sets. Kakeya sets can compress a little bit, so your constant needs to blow up a little bit. Okay, and then in order to prove this is like saying that the measure of the directions is bounded by E. We have the change of variables for it. So this is just the definition of the measure, or we can write it like this. We just integrate over all these points y on the set. And then because this function g is at least 1 to 1, we know that this is always bigger than this. And then we can just integrate over this. This doesn't depend on t. T, I might refer to it as time, but really it's just the xn axis going up the way. So this doesn't depend on the xn, this only depends on these variables. And so I can integrate in t for free over an interval of length 1/4 and then by multiplying by 4. And then the proof goes that somehow we want to bound the directions by the lines again. So I just add this in and then we'll see if this is possible or not in a moment. And then if this were 1 to 1, we would have this inequality, but it's not. And we'll come back to that in a moment. And then finally, so this is now just the slice, the t slice of the lines at height t, and the measure, and then we integrate over the heights. And so these are all inside t. These are the lines. Initial position plus t times the direction of t. The hypothesis of the theorem is that these lines are inside E. And so this is bounded by this. And in order just to fix up things, to finish, so why is this true? This is not true. This is the determinant of the Jacobian, right? And for fixed x, this is a polynomial of degree n-1 in t. So it has roots. And moreover, this is the polynomial of degree n-1, and the leading coefficient is precisely this. So when t is a root, then this is equal to 0 and this is not equal to 0. So this does not bound this. However, for most of the points in the interval are far away from the roots. And so for most of so we can choose this interval precisely to be away from the roots, and then this is true. Just paying with some factor. And then we do Fubini's theorem. And now we're back to this thing. Can we bound this by this? Because this is a polynomial of degree d, so before we had that this was this divided by d to the n is less than or equal to this, so we're n minus 1 dimensions now, so you could put this over 1 over d to the n has come over to this side. And that's it. And something to remember for later is that, so here we're kind of assuming that each of the tubes is at least half of the tube of each tube is inside this set. However, you may be in the situation where only a lambda fraction, so lambda, a small number, of each tube is inside E. Can you say anything then? And you can. Then all you do is you do some pigeonholing and so on so that you get things at the same height. And then this interval now is just lambda over 2 because we only have half of the points are going to be well behaved. So then instead of multiplying by 4, because we have quarter here, we multiply by 2 over lambda. So we lose some factor of lambda, because this is a small number, remember. But also here, when you're saying that t is far away from the roots, if the interval is very small, if this is a small interval, then the n minus 1 roots could be quite close together. And so when you multiply, the multiplying factor in order to make this true also depends on the size of the interval. And so basically the only thing, it's this exactly the same calculation, but you lose a factor of lambda to the n, 1 over lambda to the n. So, and that's as good as you can hope for. So basically there are more, the bound that you get on the number of tubes that can be inside, if they're less inside than more tubes, there can be more tubes. Okay, so
just one question. So here, the length of this interval Ix, it's independent of x.
Yes, absolutely. But it's a different choice of interval for each x, because for different x, this is a different polynomial. So the roots are in different places. So you choose a different, you have the same length for each x, but you just choose, you're choosing this interval so that it's away from the roots of this polynomial.
Mm-hmm. Okay.
Same length, the same.
Yeah. Okay. Mm-hmm.
Yeah, and one more question about this lambda. I mean, in this set E, we could also have like something like cone type structure somewhere. So I'm somehow missing that. How does one choose this lambda? So that, you know, some fraction of the tube is inside the set.
Yeah.
So could you please say a little more about it, or?
I will do later. Well, I can just flip ahead. So what I mean is this, so yeah, if this is a cone, for example, then all we're saying is that when you look at the intersection between the cone and the tube, then it needs to be at least as big as lambda times the tube. So you have a lambda proportion of the tube inside the cone, and then you have the same inequality, but you lose this power.
Okay. 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 Thank you.
Which is, so this is the one we proved originally, but this is the one we will actually use, because when we apply this to the Kakeya problem, we won't generally have this property that the tubes are completely contained in here. We will have that they are somehow contained, partially contained. Okay, so we talked about, so this inequality, the inequality we just looked at is very good for, well, if you don't have the semi-algebraic condition, That's good for the to prove that the Minkowski dimension is bounded below of a Kakeya set. But we'll also consider the Hausdorff measure. So the Hausdorff measure, the Hausdorff dimension is defined like this. So you take your set, you cover it with balls of radius delta I, of radius, of a radius less than delta. And then you sum up these alpha powers of the radius. And you take the smallest possible cover of all the covers. You take the thing which makes this smallest, and then because this is as delta goes to 0, then this condition is harder. So this is growing, and so the limit exists, and so that's what we call the alpha Hausdorff measure. And the alpha Hausdorff dimension is where this is finite, or at least the point where it jumps from infinity to 0. So if you think of this as just a line, and then you're going to have, and you're covering it with delta balls, you're going to have delta to the -1 in the sum. And so you better have alpha equal to 1, because otherwise if it's 0, then this is just 1, and then you have delta to the -1, which is going to go to infinity. And if it's too large, then these small powers to a high number are too small. And so it jumps from infinity down to 0. And then the point where it's just right is the Hausdorff dimension. Okay, and the Minkowski dimension of a set is always greater than or equal to the Hausdorff dimension of a set. So if you can prove that, remember we're trying to prove that Kakeya sets have dimension n, where n is the ambient dimension. So it's easier to prove that the Minkowski dimension is n than the Hausdorff dimension is n. So a slightly stronger version of the conjecture, or I don't know if it's slightly or much stronger version of the conjecture, is to say that the Hausdorff dimension of a Kakeya set is bounded below by n. So, or is equal to n. So this is the inequality that would tell us that the Minkowski dimension is greater than or equal to n, because you can take E to be the delta neighborhood of the set, and then you can find delta to the -n-1 different delta separated tubes inside that E. And so then this is equal to 1, and you're saying that the delta neighborhood is bounded below by 1. Of course, for the Kakeya conjecture, you need this delta to the -epsilon here, because we have seen that they will compress a little bit. However, a stronger version of the conjecture is the following. So remember, I remind you that this is true, that this is because if you take the norm out, the sum outside, then the integral of the tube is just of this volume, and then you sum up, and so this is to the power p, and then you can just do Helder's inequality. These tubes are also, all of this is supported in E, so you can just get the support out and then go up to LP. And so if you could prove this, then you can bound this guy by this guy, and then divide through by this guy, and then you have E to the power p minus 1 bigger than or equal to this to the power p minus 1. And you have this constant also here, but note that when p is equal to n over n minus 1, n over n minus 1, this becomes n, and this is 0. So again, we need some minus epsilon here for this to be true. And so this is stronger. This is clearly stronger than this. And moreover, Bourgain proved that if you can prove this, then that immediately implies that the Hausdorff dimension of the Kakeya set is greater than or equal to p prime. Now, p prime of this guy is n. So p prime is the Helder, the dual exponent. So 1 over p plus 1 over p prime is equal to 1. So, there's different story for this one. So, for instance, Davies proved the Kakeya conjecture, set conjecture. He proved that the Hausdorff dimension of a Kakeya set in 2 dimensions is 2. But Cordova proved this one, which is the stronger. Then, so the game is to get this P low, because when P is too high, then if P is very high, then this is not equal to 0. This number is not equal to 0. And we have some delta power here that we don't want. But 2 is, in 2 dimensions, 2 is the correct number, 2 over 1. And so the game is to get P as low as possible towards this. And so many people, well, not too many people have contributed, to be honest. So Drury and Crest got it down to here. There's also another paper of Christovan de Coachea and Rui de Francia. And then Bourgain improved it. And then Wolf improved that. These were somehow geometric arguments, if you like. These involve bushes and hair brushes. So if you think of lines going through lines, you can do things. And then there was these improvements. These are only improvements in high dimensions by Bourgain and Katz. This involved arithmetic combinatorics, sort of slicing the Kakeya set and looking at arithmetic progressions inside it. And then more recently, there's this improvement with Guth Zahl, and that involved polynomial stuff. That's where this conjecture came from. And then that was recently improved by Katz and Zahl. And this is the best bound in 3 dimensions due to Wolf, and they also proved that the Hausdorff dimension can be improved very slightly. And so we're going to make some improvement in intermediate dimensions. So this is high dimensions, this is low dimensions, and we're going to get something in between. First of all, eventually we'll do good in all higher dimensions. Okay, so this is what we get just using the polynomial Wolf axioms, and so we get in roughly 100 dimensions, all the way up to 98 dimensions, we get some improvement, but because we get some P which is smaller than the previously known P, but in higher dimensions, so this alpha n. So this, we're looking to prove that this is true with an alpha n equal to 1, right? And so you can also think of how low can you make this coefficient go? And so with our first attempt at using just the polynomial Wolf axioms, and this was in collaboration with Jonathan Hickman, we managed to get it down this lower than what was known, lower than 7/4 for intermediate dimensions, but higher than 7/4 all in all dimensions, if you like. So we got lucky in the middle, if you like. Okay, so, and this is going to use this polynomial stuff. Okay, so let's try and prove some, some of the proof of this. So first of all, I should give some history of where the polynomials came from. So Wolf came up with a finite field version of this. So this is, you can think of a finite field to the power n, and then lines inside there. And if you take, so there's q points in each line. So this is, before this was the volume of the delta tube. Now this is like the cardinality of the line. So the set which contains all these lines should always be bigger than or equal to this, is the conjecture. So if you take, you can have q to the n minus 1 lines. So that q times by q to the n minus 1 is q to the n. So what we're saying is essentially this fills the whole space. Not quite, but you know, you have some constant. But you're saying that if you take lines in every direction, they've got to fill up the whole space in some sense. And De Vere proved this using polynomials. And then Ellenberg, Oberlin, Tau did the maximal version, also using polynomials. Then there was a bunch of work. This is all kind of, so this is a kind of discrete Kakeya problem. And these are also kind of, sorry, not this one and not this one, but these ones are kind of discrete Kakeya problems. And what the initial polynomial method of De Vere was to put an algebraic variety through all the points and use that, then use the fact that there's lines to then you, in the fundamental theorem of algebra, to say that the polynomial must be 0 and that reach contradiction. So these works all put the algebraic variety through the points, if you like. Whereas there was a very important piece of work by Guth and Katz solving the Erdős distance problem in 2 dimensions, where they stopped putting the polynomials through the points and they partitioned the space with the polynomials. And so that's somehow the root of why we were looking at these semi-algebraic sets. Well, I'll come to that in a moment, because this was discrete. So so here you had a partition of the space into cells, which are the algebraic variety will divide the set up. So the algebraic variety will divide the set up into, so this is the algebraic variety, and these are the cells, and this is the wall. However, that's appropriate when the lines are genuinely lines. When we're dealing with tubes, so you really want to, so one of the key tricks is to use the fundamental theorem of algebra to say that a line can only cross this so many times, the degree of the polynomial. But you can't say that about a tube, because a tube could run through here, and then it's not necessarily a line. Sorry, this is terrible. It's not necessarily true that the core line is going through the algebraic variety. So you can't necessarily use it might just be that part of the thickening has gone in, right? And so in order to fix that problem, you look at a delta neighborhood of the algebraic variety. And then when you look at a delta neighborhood of the algebraic variety, all of a sudden, you're not talking about an algebraic variety, you're talking about a semi-algebraic set. Anyway, so Guth did that for the first time in these restriction papers. And there's been other work since. So I can leave that there, okay. I don't know if that's helpful. Okay, so how do we do polynomial partitioning? We use the polynomial ham-sandwich theorem, which comes from the Boursac-Ulam theorem. So this is a continuous function which maps from the k-dimensional sphere. So this lives in Rk plus 1. And it maps down to Rk, and it's continuous, and it has this odd property. Well, then there exists a point. I've written p sub k, but this is not the kth. It's not. I mean that this is just. So think of this as p0. There exists a point on the sphere which is mapping to 0. So that's a bit like the intermediate value theorem, that if it's continuous and you have this odd behavior, then there must be a point where it hits 0. And so a theorem of Stone and Tukey applied this Borsuk-Ulam theorem. Well, I assume this is their proof, but maybe it's not. I read this in Guth's paper. So for any family of K sets, there is a polynomial and a variety which will bisect each of the K subsets into two pieces of equal measure. Now, measure here can be Lebesgue measure or any measure which is absolutely continuous with respect to Lebesgue measure. And so how do you use the Borsuk-Ulam theorem to prove the Stone-Tukey theorem? So first of all, you identify all the polynomials of degree D. So we can do with points in this set. So you take the coefficients of the polynomial and you put them into the different slots of this vector. Now, of course, there's a lot. You need some kind of precise relationship between K and N and the degree D. So K is a lot bigger than N. It's a lot bigger than the degree. But I don't want to go into that. So, and then you define the jth coordinate of this F by, so eventually we're going to restrict to the sphere, but it's a function from here to here by, so the jth coordinate, so this is a vector, so you have F1 going into the first slot, F2 going into Fj going into the jth slot, and it takes this point, which is the same thing as the polynomial, to this value. The measure of the set intersect p greater than 0 and the measure minus the set p less than 0. So if you think about it, f of p must be the negative of f of minus p, because then you're taking negative p's, and so you just change the role of this and this, because minus p less than 0 is the same as p greater than 0. So it changes the value, and so then we can apply Borsuk-Ulam to the restriction of this to this, and we find a point where it's 0, and that gives you a polynomial where this is 0. So we found the polynomial which is for the point where this is exactly the same as this, which is what we mean by saying that p equals to 0 bisects the set in two pieces of equal measure. So that's the polynomial ham sandwich theorem, and then you can use that to so what the measure that we're interested in is this, of course, the LP norm of these functions. And so any subset of Rn can be divided into 2 to the j subsets of equal measure by some algebraic variety. So how do you do that? You just start with a set. You start with a set. Here's a set. And then we find this polynomial, which will divide it in 2 with equal measure with respect to this measure. And then we find the polynomial, which will divide these 2 sets into sets of equal measure. There's another one. And then we find that the polynomial which will divide these 4 sets into sets of equal measure. And so there's the other algebraic variety. And so if you look at p, if you multiply all those polynomials together, p equaling 0 is the union of all these. So we find so that this single algebraic variety has divided these sets into 8 pieces of equal measure. And so you can keep doing that. And so there is this relationship between the degree of the polynomial and the number of the pieces I've been brushing under the carpet. But now I tell you that you can roughly do this. It's not quite true, but almost true, that with some constants. Again, I don't want to keep the constants. So see you have d to the n, if your polynomial is of degree less than degree d, then you have d to the n number of pieces. Or you can do it, you can cut it into d to the n pieces with a polynomial of degree less than d. That's the correct way to say it, or almost correct way to say it. So we're going to use that to divide up this norm. And so that's the first step of the proof of this Kakeya maximal estimate. So for any large d, we can find a polynomial of degree d or degree less than d, such that this norm can be divided up into, so remember, these guys all have the same measure with respect to this measure. So we've done this so that these are all exactly the same size. And this O prime is a cell, and it denotes a piece, one of these guys, right? And each of these summands is equal. Now, as I was saying, we want to remove, if we think of E as being the delta neighborhood of this algebraic variety, we call that the wall. And so now we think of these shrunken cells, so we have to remove this E from each of the cells. So instead of looking like this, we look like this. And that's still just a partition, right? Now, as I was trying to explain here, by the fundamental theorem of algebra, a line can only cross this, cross these pink lines d times. So if here we only need to think of also, instead of thinking of all the tubes, you only need to think, of course, of the tubes which enter the cell. Now, and here, so there's an abusive notation here, because before I told you that this means that the tubes are inside E, and now I'm telling you it just means they intersect O. So they intersect it. So there's definitely some details I'm hiding, but we'll ignore that. So because a tube crossing can only cross this wall if the core line is crossing the algebraic variety, then you know that you're only, when you add up all these different tubes, you're counting, some tubes hit more than one cell, but they cannot hit more than, in fact, they can hit d+1 cells because they can cross this d times. I just write d because I don't care about constants. And so by the fundamental theorem of algebra, you know that no tube is intersecting more than d+1 cells. So we have this. And moreover, we have this sort of supremum bound, because if this were not true, if most of the number of tubes hitting each cell was greater than 4, you have d to the n number here. So you would have that this would add up to more than this. So we know that for most of the cells, we have this bound as well. And then we will use the polynomial Wolf axioms to deal with this guy, because the tubes are somehow contained in E, somehow contained in a semi-algebraic set. So what more, right? So now I want to tell you, I don't want to tell you too much about this at the moment. Well, somehow I've already told you about this. So what about when the non-algebraic case, when the tubes are not clustering inside the semi-algebraic set, they're somehow just smashing through the cells willy-nilly. So what we mean by that is that this is bigger than this. If this is bigger than this, then we can throw that one away and just put a 2 here. So I've put 4 here, Probably because I'm going to tell you something else. Oh yeah, so also when we remove the wall, these are no longer exactly the same size. These were exactly the same size. When we remove the wall, some of these might get very small, but we can throw, most of them have to be quite big in this, because this contains most of the mass of this. So most of the cells must remain quite big. So we can throw away the small ones, and then we still know that these guys have roughly the same size. By just times them by 2 again. And then also this was that we have this inequality for most of the cells. If we throw away the ones where it's not true and then multiply by 2 again, we still have this. And so finally, right. And so imagine we're in the case where then we repeat the process. So that instead of starting with this original set or Rn, we start with, these are compactly supported. So this was a set, not Rn. And then we repeat the whole process on this on each of these cells. So with the same fixed d, we find another polynomial which will divide up this cell into another d to the n pieces. And if, again, the cellular parts are dominating the wall parts, then all that's happened is we write this 8 squared, and then if a line can intersect d of these guys and then d of the guys in here, so it becomes d squared here, and this becomes squared as well. If we do it k times, we just go up and up and up and up. And this is what I'm talking about, the non-algebraic case, when it keeps dominating where we don't find tubes clustering around these walls. We just keep finding that the dominant part is the cellular part. So finally, we know that the number of tubes that we start with is bounded by delta to the, you can never have more than this number of delta separated tubes. And so the supremum over all the cells is bounded by this. So I'm going to need these 3 inequalities in the next slide to complete the proof of the non-algebraic case. So somehow it's a balancing act between the non-algebraic case and the algebraic case. When the wall dominates, we'll talk about that again in a moment. And this is when the cells dominate. So imagine these cells keep getting smaller as well. Imagine the measure is very, very small after k steps. Now, also, I want to bring to your attention that if we keep cutting, this starts cutting and it gets this small, then of course this 8 to the k is also getting massive, right? So this is not just, I mean, I don't like constants, but this constant, you have to take care of it. So, you know, this could easily be some power of delta, right? So, but if you get to the stage where you just keep going down and the cells just keep getting smaller, then you can bound this LP norm very, very trivially. The supremum norm of this is just the number of the tubes. And then the measure of this is delta to the n. And so you have this bound. Nothing more trivial than that. And then what we do is however, we break this up. We pull some power, this to the power p. We can take p minus 1, the supremum, the worst one of all the cells, and then leave the other power of 1 inside this sum. And remember, we have these 2 bounds, which essentially come from, well, they do come from the fundamental theorem of algebra. That's just, so these are the 3 inequalities that we established on the previous slide. So now we just stick this in here, and this guy in here, and we get exactly this. So nothing happened there. And now we manipulate, we rearrange things. We want to group together these k terms. So remember, this is very dangerous. This is also very dangerous. And the only thing that can save us is this guy. So we get the k guys together. So this is an identity. This is 4 to the power p minus 1 comes out. That's a constant. We don't care about that guy. 8 to the k. That's 8 to the k. And then d n minus 1 to the power p is this part. And then you've also got n minus 1 coming from here. And then you add 1 and then you get that. And then similarly, you just get this guy together with this guy. This guy. So minus n minus 1 to the minus 1 is this guy. And then p is this guy. And then this guy is this guy. So that's just an identity. And this is exactly the constant we were looking for. This is exactly what we want on the right-hand side. But what about this guy? All we need to do is choose the degree of the polynomial from the beginning, which just means we're taking more and more and more pieces, but the point is, if p is bigger than n over n minus 1, this is a negative power. And so you take the degree of the polynomial, the initial degree, which is a choice that you make at the beginning, just take it so that this number is bigger than 8, smaller than 1 over 8. So that means that this whole thing is bounded by 1, and so to the power k is not a problem. And we're done. So this, we see here that the only way we can do this argument if p is bigger than n over n minus 1, which is great because we know that you can't prove the Kakeya maximal conjecture below that p. So that's good. So in the non-algebraic case, we're done, right? Whatever that means. But of course, what can happen is at some stage, as you're going along this iteration, we find that the walls dominate. And what do we do then? What we do is we drop down dimension into instead of being in, so here we're in 2 dimensions, but here, once we're inside here, we're like in 1 dimension. And then we which is not a great thing to talk about when you need to have tubes inside here, but think of in higher dimensions, right? So you go from 3 dimensions, you've dropped down to something which looks more like a plane, but you can still have tubes inside the plane. Now, what happens then is you just keep doing the process. You start polynomial partitioning inside the variety, if you like. And what happens is all of this calculation is still valid, but certain things change. Essentially, all that happens is that the ambient dimension goes from n to m. Here, we're actually using the polynomial Wolf axioms because I'll show you how in a moment. Because before, remember, I said that the total number of tubes can never be more than minus n minus 1. Well, the total number of tubes inside a delta neighborhood of an m-dimensional variety is this big and we know that because of the polynomial Wolf axioms. I'll show you why in a moment. But anyway, what's happened is all the n's have changed to m. Now, why is that a problem? It's good because this p, basically, in order to close the induction now, we need p to be bigger than m over m minus 1, which is a bigger number. So, but it's not the end of the world because at this number, this is still 0. And so what you do is every time you drop down a dimension, so imagine we've dropped at this point, we have lots of different walls dominating. All you do is you do some kind of Hölder's inequality to raise the Lebesgue exponent. And then you can keep working with this guy. Now you're in a lower dimensional situation, but you've raised the Q. And then you can use a trivial estimate for this L1 norm. Again, you just pull the norm out, you get the number, the sum out, you get the number, and then the volume of each tube is like this. And actually, because these cells are getting smaller, a tube cannot, the whole, as you integrate over the cell, I wish I could annotate. I've lost the capacity. Here we go. So here's your tube. And there's your cell. So it's delta n minus 1 here. But instead of times them by 1, we can actually also, you're not getting the whole tube, you're only getting this part of the tube. So you get some small gain there. Now this diameter of the cells is important, as we'll see in a moment. Is there anything else I wanted to say? Well, I should also mention that I'm brushing other things under the carpet, that somehow you can keep going, but you need to keep, and every time you go down, you need to when you're doing these kind of interpolations, you need to make sure that you're able to close the induction at each level. And so if you go down many levels, you're somehow in a worse state, because you need to maintain a lot of energy to close all these inductions. So actually, this is done not with LP norms, but with multilinear norms. And you know that when you go to a certain level, when you drop down too many dimensions, then they become 0. So then you know a priori that you're not going to have to drop down too many times. And so you can use some of that inductive energy to improve the piece. And then there's an argument due to Bourgain and Guth to convert these multilinear norms into the linear norms. But essentially, that's how it's done. Oh yeah, and something else I wanted to say was something about how we're dealing with. Another thing we need to look out for is that there's other variables are coming into this thing. So you need to look out for the inductive. You need to look out for these guys anyway, but there's other things coming into the equation, right? For instance, here, I'm bounding this guy by delta to the minus m minus 1. So first of all, I'm going to explain to you why that's true. But because really these tubes are not contained in these cells, they're not contained at all. You know, the cells are already smaller than the length of the tubes. We're losing, if the size of this is lambda, we're also losing powers of lambda. Remember, we had a power. If this is lambda, if the size of this, I'm not good at drawing. If the length of this is lambda, then in here we're also losing a power of lambda to the minus n, as we saw earlier. And we need to make sure they're small number. Well, lambda to the minus n is a big number. We need to make sure they're also not showing up in a nasty way. Anyway, I have to delete that guy. So these are the two polynomial Wolf axiom theorems I told you about before. I said this one, and I'm glad we've already talked about this one. Because this is really the one we use, because the tubes are never completely contained. This E is the delta neighborhood of an algebraic variety intersected with a ball, generally a small ball of radius lambda. And so it can never be fully contained, it can only be lambda contained. And so we're going to lose these powers along the way. And so really what we look at, in order to prove the Kakeya maximal estimate, we're taking these algebraic sets, these semi-algebraic sets, to be delta neighborhoods, actually 5 delta neighborhoods of lower dimensional algebraic varieties intersected with a ball of radius lambda. And so we do lose these powers, which is a nuisance, and we need to deal with them. But also, I'd just like to point out what we used at one stage was a bound on the number of tubes inside this delta neighborhood. And how do we do that? We use Wonku's lemma to bound the volume of this. The volume of this, imagine that this was an m-dimensional plane. Well, I'll just quickly move on. So the Wonku's lemma bounds this measure. So basically, this just tells you that if this was an n-dimensional hyperplane, then there's the codimension, and this is the delta neighborhood, then the delta neighborhood shows up in the codimension, and then this is the ball restricts within the n-dimensional, so that the lambda radius of the ball shows up here. So that's what you'd expect, but you need to prove it. And one could prove that. And so you sub that in. This is the inequality we had before. By subbing it this into here, you get this lambda m goes with this lambda minus n. So you get n minus m here. So actually, that's what we were losing inside the previous calculation. And then the delta to the n minus 1, you can take that across, and n minus 1 times by m minus n here gives you this. So this is what, so in the previous calculation, really, let me quickly go back to it. Really here we're losing a lambda to the minus n minus m, and this is where the delta to the minus m comes from. Sorry. So this theorem gives you a bound on this, the number inside the delta neighborhood of the algebraic variety. But these lambdas can be improved. So next time, basically, I'll show you how to improve on all of this by using more of the geometric information available to us, giving us better powers of lambda, if you like, so that we can use, so that we don't lose as much inside the induction argument, the iteration. And I'll also move on to the Fourier analysis side of all of this. Okay, I think I'll stop there.
Okay, thanks you. So are there any questions?
Yeah, this involves a lot of things. It's completely new for me. I was wondering, like this Kakeya conjecture, here you consider all possible directions. So are questions where people consider some infinitely many specified directions also, and try to understand sets which contain those?
Yeah. So this is due. Why is this called Kakeya maximal? This is because you can make this into a maximal estimate.
Yes.
So this is p prime. So this is n over n minus 1, and so the maximal estimate is an ln, and that is like the Hardy-Littlewood maximal operator, but instead of averaging over balls, you're averaging over these delta tubes. Now, in that context, yeah, people have thought about different questions. So for this Kakeya conjecture, the delta tubes are all sort of separated, the directions are separated by an equal amount. And so you always have a sort of finite number of tubes. However, you don't need to average over delta tubes either. You can average over just lines. And then you can consider an infinite number of directions if, for instance, you take the directions to be different, but lacunarily. They're not all, the difference direction is not the same. And then you can prove LP bounds without these losses, because those maximal, this guy, the maximal operator associated to this will decompress a Kakeya set. So you can't have LP bounds for that maximal operator. However, with infinite directions, you need to lose some power of delta. However, when you take lacunary directions, you don't need to, that maximal operator will not decompress the Kakeya set. And so you don't need to lose a power of delta, and you can have LP bounds with infinite directions.
I see. Okay, that's very interesting. Okay.
And so that kind of work was started by Sjogren, Cordova and Pfefferman, and there's a great paper by Stein, Stein and Wanger, and also I have a paper with Arset about that kind of question in higher dimensions. So a lot was done in 2 dimensions, but lately things have moved into higher dimensions as well.
I see. So it's like lacunary directions and maybe more. That's what you're saying?
Yeah, different notions of lacunarity. Basically, somehow it's basically true that if you have infinite directions, they need to be lacunary in order to have LP bounds.
Okay.
What do I mean by lacunary? In higher dimensions, it's not so obvious what lacunary means, and so on and so forth.
Yeah, thank you.
And also, if one if there is a Kakeya set which has which contains tubes in all the directions, can one just restrict to some particular sector and work, or it's the same?
If you restrict to a variety, then it's like you've just gone to the lower dimensional problem. Yeah. I mean, essentially, that's what these kind of things are telling you. That, well, for instance, I'm not entirely sure, but like, for instance, this argument, you can do it in a lower dimensional variety, and it's just the same as if you started in a lower dimensional space.
Yeah. Yeah, so here, I mean, as you mentioned that you also use some multilinear estimates, right?
Yeah.
Induction argument, I suppose.
Well, this is kind of the induction argument, but really we're not doing it for LP norms, we're doing it for multilinear norms, where it's the LP norm of products of different sets where the tubes, you know that in a priori that so if you have the product of this guy times by another guy, similar guy, but with different tubes, then the condition is that they're transverse, that all the tubes from one set are roughly going in this direction, and all the tubes in the other function are roughly going in this direction. And so then, of course, the intersection of the tubes, these tubes with these tubes, is much smaller, as we saw in the first lecture. So that obviously it's much easier to deal with that kind of object. And the surprising thing is, so those kind of estimates were first proved by Bennett, Carberry, and Tao. And then Bourgain and Guth found a way to prove linear estimates for this kind of guy with using those multilinear estimates. So really we work with the multilinear estimates, and then we build back to here using this argument due to Porcana and Guth.
Okay. Are there any questions?
So just one more query. So when you decompose the set into these cells, and then basically you iterate the process with each cell. So is it like, you're fixing a scale and then getting an appropriate decay in the next level and so on? That is what is happening here, because you're counting the how many the tube is going to hit how many cells. So the measure is going to also go down.
Yeah. So basically, this kind of thing tells you that somehow it's a good thing that nothing happened. That because eventually, it's completely trivial. The Kakeya, this norm is very easily bounded when this is very, very small. And the reason you wouldn't normally do this is because, of course, this is a disaster, right? You're not getting kind of reasonable constant. And the miracle is that somehow you can kill it. So this kind of argument was that this kind of argument was done, I guess, by Guth and Katz in the context of the Erdős problem first, and then Guth in the context of the restriction problem, which we'll see a bit about next week. I mean, they write it as an induction argument, actually, but in order to put this information inside the induction argument at different points, we wrote out as a recursive algorithm.
Actually, for me, the difficulty is like we have a set and then we decompose into infinitely many things, each of which has the same measure with respect to this function. So I'm sorry, I couldn't really understand like how does that really help? But I think this calculation one has to go through. Yeah.
I guess it helps basically because eventually you have this bound.
Yeah. Then basically you're compensating for this 8 raised to the power k. That is what is coming up. The later.
This decay allows us to do this. So basically, if this keeps happening, then it's good because it's easy to bound and we can deal with this. And then if it doesn't happen, then it's also good because then we move down dimension and we understand the Kakeya problem in lower dimensions. Eventually you come to a one-dimensional set and there's only one tube inside one. So then it becomes very, very easy. So you win either way.
Yeah. Okay. Yeah, this is very interesting. Thank you.
And also the choice of D is also in some, I mean, you can choose that, right? I mean,
yeah, like
that also helps, I suppose.
Yeah, the fact that that's absolutely right. Yeah, because you need to choose it. Very, if P is very close to n minus 1, you need to choose very, very large.
Yeah.
But still, well, I say very, very large, but still low degree in some sense, still extremely finite.
Yeah, that's amazing actually how you use this sort of decomposition. Yeah.
I agree. I mean, and this is I think it's an extraordinary thing, but I didn't. It's not my idea. In this context, I had something to do with it. But I mean, these arguments are very similar, especially to what we meant for restriction. This part of the argument.
Yeah. So these kind of things one can apply on the cone also, I suppose. I mean, this sort of decomposition for the restriction. I mean, maybe I'm jumping a little bit, Because I've seen people using arguments on the sphere or non-zero curvature, which you will mention next week, I suppose.
Yeah, well, maybe I won't talk too much about it. Yeah, but so but when you drop down a dimension, you do exactly the same kind of argument on the variety, and that's more, that requires work to prove that everything is okay there. Like, but yeah, people just keep working on the variety as if it were Rm rather than an m-dimensional variety.
Okay. Yeah, okay. So if there are no more questions, let's thank the speaker for introducing us to a really upcoming and very exciting topic. Yeah, so thanks. And yeah, so we'll meet you next week. Sorry, I'm not able to hear you.
Sorry?
So yeah, I'm saying that so we'll see you next week.
Yes.
Yeah. Okay.
You also want me to send you the second
Yes. Yeah.
slides, but can I send them tomorrow?
Yeah, sure. You can send them tomorrow. No problem. Yeah. Okay. So
Okay.
yeah. Bye.
Bye.